Well, welcome back to the office again. Today we'll talk about what? I don't know. Electromagnetic waves. Okay, so we'll talk about the finite difference time domain algorithm, the FDTD. So there's really not that much new in the world in general, and here we'll just talk about waves again. So you should have studied, listened to the lectures, mastered something about the wave equation already, because we'll be solving a wave equation, but we'll be solving one now for electromagnetic waves. So it's a little more complicated, but the basic idea of the algorithm is the same. So what do we have to do? Well, we have a problem. What's your problem? Tell me no problem. You don't have to tell me a problem. Okay. So here we have a problem. We're asked to determine the electric and magnetic fields, the E and H fields, for all possible times. Okay, that's quite a challenge. We're given a region of space, okay, Z, from 0 to 200. So we have a finite region of space. Without a finite region of space, you can't solve the partial differential equation. You have to have boundary conditions. You have to have boundaries. So we have boundaries. And we're told the initial conditions, here in red, the initial conditions is that the electric field is in the x direction only at time 0, and as a function of Z, it has a sinusoidal form. Simultaneously, the magnetic field, the H field, is in the y direction, and we have at time 0 also a sinusoidal variation with Z. So that is the problem. Okay, so the problems of this sort, electromagnetic problems, have tremendous practical importance. They're used for electromagnetic waves. They're used to produce devices. We'll do, of course, a very simple free field here. There's no sources. We don't have to worry about charges or currents. And we don't have any real boundary conditions. We haven't done a waveguide. But once you know how to do this problem, once you know how to solve the Maxwell's equations, exactly what the boundary conditions are, exactly what the medium is, it could be some of these newfangled materials that have layer upon layer of dielectrics, we can just solve it. Just let the computer do the solving. So we'll just worry about the hard part today, how do you solve it, and leave the technology to others. So this is our problem. As I stumbled over at the beginning, this is called the FDTD method. People are always making up new names for them to think what they're doing is different from what others have done. It's not. FD means finite difference. Why? Well, because we'll have finite differences for space, delta Z, and we'll have finite differences for time, delta T. That's the finite difference. But we're not just doing space, so it's also the time domain. So that's where the name comes, finite difference out, and also including the time domain. No big thing. The wave equations we solved all had the same space and time together. Okay, so that part is all old hat to you. Read the wave equations before you continue if you haven't already. What is new here is we have two aspects which are quite different. One, we have coupled fields. Okay, so we don't just have one disturbance. We have both an electric field, which is a disturbance, and we have a magnetic field, or an H field, which is a disturbance. And they're coupled together in this way that electric fields like to do. That's new. Secondly, we have a vector field. In fact, we have a whole vector problem. And this is new. It's more complicated. If you love subscripts and superscripts, you're in heaven now. If not, you have to deal with more complications. It's truly a three-dimensional problem, even though we're trying to keep it simple. What do we mean by three dimensions? Well, we have propagation in the z direction. Okay? And this is one of those diagrams which drive elementary physics students crazy, because we're really plotting different things in different places, different quantities, all on one diagram. This is space, fine. In the x direction of space here, upwards, and in red, we have an electric field which only oscillates in the x direction. And in the y direction here, coming out of the plane, we have the magnetic field, which only oscillates in the y direction. Or at least initially, we're told that. We don't know if that'll be true forever until we look at some of the laws of physics. So what we see here in this diagram is an initial pulse, like a sine wave, and then as time moves along, this pulse moves along the z-axis. Okay? Of course, we don't have a pulse here. We could do a pulse, but we're doing a sine wave, so we have a whole sine wave that moves. So we have to see if that gets propagated through space or what. I mean, you know, since we're calling it waves, it obviously is going to get propagated through space, but we have to see if the algorithm does that, if it all works. So this is what's new. It's truly a three-dimensional problem, and so we have a few interesting complications and a few clever tricks. So let's get going. Look at the next slide. Study it. Take it home. Okay. So what's the theory? The theory of electromagnetic waves is Maxwell's equations. Fortunately, we're in free space. We have no currents. We have no charges. So we have a simple problem. We're also told that the electric field, which could have y and z components itself, only has an x component, at least initially. And as we'll see, the physics is such that we only have to worry about the x component. It just stays in the x direction. The magnetic field, likewise, just stays in the y direction. So yes, they're vectors, but they only have one component each in a different direction. So that makes life a little simpler. The pointing vector, E cross H, the vector which tells you in which direction power flows, well, if you just work the right-hand rule, E cross H, goes in the z direction. Okay, so power goes along the z-axis here, as we'd expect. That's the direction which the wave propagates. Fine. Okay. The first Maxwell equation we have to deal with is something like the divergence of E is equal to 0. Okay, so there's no charges present. There's nothing on the right-hand side. That just tells us, if we translate that for our problem where the only variation really is in the z direction, it tells us that the derivative of E sub x, the x field, the electric field in the x direction, is 0 with respect to x. So we have a transverse wave. As long as we just have movement in the z direction, the electric field have no variation, is a constant in the x direction. So we don't have to worry about how it varies with x. Likewise, the magnetic field H has no divergence, and that means that its derivative with respect to spatial dimension y is 0 as well. So we have a transverse wave in both the magnetic and electric fields, transverse to the z direction, and that's enough, equations 1 and 2. That's enough to forget about equations 1 and 2. As long as we remember we have a transverse wave, we only have third and fourth Maxwell equations to worry about. So what are they? Aha. So this at least involves space and time. So these are the equations which can give us a wave, because that's the unique aspect of a wave, after all. So the Maxwell equation, which tells us that the time derivative of the electric field is given proportional to the curl of the magnetic field. So in other words, time derivative of the electric field is determined by the spatial derivatives of the magnetic field. This sort of funny coupling. Explicitly just comes a simple equation. The derivative of E with respect to time is proportional to the derivative of H with respect to space, Z. So the two are related here. And if you look at that equation, it looks like a one-dimensional wave equation. In fact, depending on how you've gone about these lectures, if you look, or if you have looked at the hydrodynamic lectures in which we spoke about convection and the continuity equation and the advection equation, you'd recognize this is essentially the form of an advection equation. Okay? The difference here is that one field is E and the other on the right-hand side is a different variable. So there's too many unknowns here to solve, but that's fine. We have another Maxwell equation up our sleeve here, and it says that the time derivative of the magnetic field, H, is now equal to 1 over minus mu sub 0, the curl of the electric field. So mu 0 is this magnetic constant of nature. Epsilon 0, the permittivity, free space, is the electric constant of nature, depending on the units you're using. But we'll see soon. We'll get rid of them, and then it'll be universal units. So equation 4 tells us the other coupled equation we have to solve, and it tells us that the time derivative of the y component of the H field, I mean, that's just too many words. So the time derivative of the magnetic field is proportional to the space derivative of the electric field. And these two together, when coupled, will give us a wave. Okay, so you can see they're just first-order equations, but essentially the coupling makes it the equivalent of a second-order equation, and that gives us the usual electromagnetic wave. So these are the equations to solve. Essentially, if we just set up the problem to be transverse, we have two simultaneous first-order partial differential equations to solve with only derivatives in space, one dimension space, just z, and one dimension in time, which is all there is in time. So how do we do it? Take a look at this next slide, or guess. We do it the usual way. Okay, we have derivatives. We can't, on the computer, evaluate the derivatives exactly, not unless we know an analytic form for all times, and that's not what we're about. So we approximate the derivatives, both the time and the space derivative, with finite differences. That's the FD, and here we're using it for time. That's the FD TD. Oh, too many letters, but you know, that's somebody else likes it. So the time, it's interesting. Look at it. It's not trivial, equation 1 and 2. It's the time derivative. It's a central difference. So we take at time t, we have a half a step ahead of time t, delta t over 2, and a half a step behind time t, delta minus delta t over 2. So this gives us the derivative with respect to time at time t. And by going back and forth between t, we get a higher order precision than if we just took one step forward. Because if we did think of Taylor series expansion of all these derivatives, by making this symmetrical form before and after, the next order, the odd terms, all cancel. So we get a higher order precision. Likewise, for the space derivative of the electric field, we have a space a half a step ahead, delta z over 2, and space a half a step behind, in space steps, minus delta z over 2. And that's the central difference. But already you can see in these two equations the one aspect which may drive students up the wall. Some of us like students on the wall, but if you don't like that, be up on the wall. Look at these equations. You can see here that the first equation has the electric field at z, whereas in the second equation the electric field is at z over 2 plus z over 2 above that, and minus z over 2 behind that. So we have, we have a half a step difference between the first and second equations in space. The same in time. The second equation, equation 2, has time t, but the first equation has time t plus delta t over 2 and t minus delta t over 2. So if you're just thinking, well, we have time and then we have delta t over 2, as the next time step, well, not really, because here it's delta t over 2, here is minus delta t over 2, so we don't just go ahead by time step delta t. It's a half step forward, half step back, both in space and in time. That sounds awfully confusing. We'll implement it. It'll work out just fine. But it means that we're sort of calculating at time t, but we're evaluating half step on either side, and then we move everything ahead. So let's make an algorithm out of this. So if we take these two expressions for the derivative and substitute them into Maxwell's equations, those are just those two equations, what do we have? We have equations in red, okay? But first we have to talk about the notation, okay? If you love superscripts and subscripts, this is heaven, right? So we have electric field. It's always the x component. So we use that as a subscript. Ignore it. Just say that's the electric field. You don't have to worry about that. Likewise, the magnetic field, be nicer if it was called M. But anyway, it's called H. The magnetic field is called H. It has a subscript y, meaning it points in the y direction. Ignore that from now on, because just remember that. The superscripts is where the action is. The superscripts represent the z value and time. So space and time, always in that order. Now you're set. So the z values can be k, or when you're going for the other variable, they could be k plus a half, meaning a half a step. So k will be an integer which varies by 0, 1, 2. It's nothing bright there, but the indices up here will have a half and a minus a half off that number to tell you which time it is. So that's this extra complication. It's just traditional. So in terms of an algorithm, we get equations 4 and 5, which means we substitute this derivative in, we look at the equations, and then we say, aha, we can get ahead in time here. So here's the time variable, the second one. We step ahead by a half to the future time by going back minus a half, so that's a full time step back. This is now, aha, the present time, and this is also now, aha, the present time. So we have present time here, we have past here, and this is the future. Okay? So that's the algorithm. We go ahead to the future by using the electric field at the past and the present values of the magnetic field. So this is how they're coupled together. So in a sense, the algorithm gives you a very good indication of how Maxwell's equations work. It's the space variation in the past of the of the magnetic field which drives the future electric field. And likewise, if we look down below, we have the time here, future time. So this is the space and time. I got that backwards. Okay. So we have here we have the magnetic field, space and time. So this is now future here. That's future time. We have on the right-hand side n, so that's present. And then we have n plus a half. Okay, so that's even more present. So this is now past, and now this is present. Okay, so we go ahead one step, half a step, with this algorithm. Okay, so it has these complications, and that's just what we need in order to solve the problem. Why do we have these complications? Why don't we just move full-time steps? Well, one could. I'll show you in the next slide how to do that. But essentially, by intermixing it this way, we get an extra degree of precision. That's what we're here for. So if we look at the next slide, we implement this by saying we have two grids. We have one grid, if you want, a space-time grid. So this is time going forward down below, and here's space going off to the right. And what we have, though, is we have in pretty circles here with white in the middle, we have the magnetic field, H sub y. Here's the magnetic field. And that says, so here's the magnetic field moving forward in time. So magnetic field is at integer values of time, and it moves ahead one time step. As you'd expect, no problem. Here are its values. However, if we look at what's being used, the electric field here, which is in the black dots, is at here integer, here integer. Electric field at integer space, but the magnetic field is at half integer space. Okay, so this is a half integer value moving ahead. So we have, in a sense, a displaced lattice for electric field and a displaced lattice by half a step for magnetic fields. But it works just as we've said. The space variation of magnetic field giving you the time variation of the electric field, and the space variation of the electric field giving you the time variation of the magnetic field. Okay, if that's too much for you, and some people don't like that, there's an alternate formulation. You can say, why don't we just get rid of all these 1/2 by multiplying everything by 2? That gets rid of 1/2. Okay, so then we have even and odd times, and that some people prefer that. And you could say that, okay, so we have the electric field at even space, and we have the magnetic field at odd space. Think of it that way. And likewise, the magnetic field at even values of time, and the electric field at odd values of time. So it's the same. They have to be out of sync a little bit for the precision. Half time step, people like that, but this works exactly the same. Okay. So let's go ahead and let's see if we can apply the algorithm. In hindsight, after trying to apply the algorithm, people have realized we could make life a lot simpler by redefining variables so that both E and H fields have the same normalization. Okay, so that's pretty clever. It also makes the stability analysis, which we'll talk about, a little more straightforward. So we'll define a new electric field, E tilde, if you want, over here. And that's just the square root of epsilon 0 divided by mu 0. So it's really something like the speed of light, but it's not the speed of light because they're in the wrong order. So it's making the electric magnetic fields the same magnitude. So in terms of that, then the algorithm becomes equations 1 and 2. So we see here, tilde, the electric field algorithm, has a beta, so a parameter, a bunch of constants in front, and the H field has a beta, a bunch of constants in front too. So now this is well balanced. It's easy to compute. And what is beta? Beta is very nice. Beta is just the fraction. It's just the ratio of the speed of light divided by this grid speed. So here's beta. C is the speed of light. In terms of the constants here, they just come together to be 1 over the square root of epsilon 0 mu 0. So regardless of which unity we're using for electric magnetic fields, once we put them in this form, everyone has to agree about a variable called the speed of light. That's what comes in here. And the denominator in beta is just delta z, the space step, divided by delta t, the time step. So it's not a real velocity, but it has the dimensions of a velocity. So that's good. So beta is what we'll use for the stability analysis. So that's handy. Let's see, what else should we say? We're going to solve these fields, electric magnetic fields, in space and time simultaneously. How big a time step do we use? Well, the answer is obvious, as is most answers when you know it, which is to say, well, whatever frequency the wave has, how many oscillations it makes in a period determines what the time step should be. Okay? So if it's a high frequency wave, you need more and more steps. So the rule of thumb is typically you always want 10 steps within each period. Fine. Likewise, what should the size of the space steps be? Well, it depends on what wavelength wave. If the wavelength is short, you need lots of small space steps. Wavelength is large, you can have larger space steps. Again, you want at least 10 points per wavelength. Okay? What about stability? Remember stability analysis? I'm not going to derive it here, but you could do it. And what you want to do is you want to say, how large can beta be before these equations lead to a growth, an exponential growth in the field? So if beta is too large, and beta, after all, is not a physical constant, it has the grid sizes in here, but if beta is too large, then the algorithm literally blows up. You just get infinity sooner or later. So that's usually not the correct answer, so you know something's wrong. So if you go through the analysis, require this to be slower than an exponential, not to be growing, you find that beta must be less than or equal to a half. Don't take my word for it. I'll assign it. You try it out. Always good to do that, even if someone else has done the analysis. Tests if your algorithm's working, and it shows you what things look like when they fail, which is always good to know. Okay? So what does that mean? It means that if you decrease the time step, a natural thing you'd think of to increase precision, it works. Smaller time step, you get a nicer wave, you get rid of the coarseness, and it makes beta smaller, because we're dividing, if you want, by a smaller number. Beta gets, we get a bigger number in the denominator, beta gets smaller. That's good. As we make delta t smaller, we also increase stability because beta gets smaller. And small beta is good for stability. So you can't go wrong by making the time step too small. You may have to wait around till you're a grandparent to get the results, but you can't go wrong as far as stability goes. Space is just the opposite. If you try to say, let's make a finer grid in space so I can see the wave varying over space, if you make delta z smaller, by itself, you make beta larger. And if you make beta larger, your solution can blow up. So you simultaneously, when you decrease the space step, you simultaneously have to decrease the time step so the two stay in sync. Other than that, let's go ahead and solve the problem. Okay. So let's look at the implementation. So here's a reminder. Here's your problem. You're given a finite region of space, z between 0 and 200, and you're told there is an initially oscillating wave, oscillating in space, because time 0, you don't know what the time variation is. So at time 0, we have a z variation of the electric field, and we have a z variation of the magnetic field. That's all you're told. Solve the problem. And you can go through the math books. That's enough. Finite region of space. You know the initial conditions. That's good. Maxwell's equations, just the algorithm we had on the previous slide, have this very simple form. It's just two very simple looking equations. First order, differences in h, differences in x. After all that talking, after all those horrendous looking equations and those complicated grids, you get down to these ridiculously simple looking equations. So this is a problem you can solve with Excel. You can solve it just almost on a sheet of paper. It's that straightforward, but there are two coupled equations. Okay? Here, 0 represents the old time, 1 represents the new time, so we don't use much memory up. These time stepping techniques, rather than solving for all times simultaneously and having a very big matrix, we just have to save the old time and the new time, and then when we're done, we save the new time, output it, it becomes old, we just continue. So it's just two variables. We just cycle through them. And in our case here, you have to decide what to do at the endpoints when you go out of the region. We'll make it periodic boundary condition, or at least in the code we give you, because then you see the wave going on forever. But you could make it a waveguide by making it stop, and then you'll get standing waves. Or see if you should. So let's look at our implementation. So here is our code. Good. So this is the code we give you for this problem. And the code looks much more complicated than it might, because we're actually trying to do a visualization in 3 dimensions. So that's, 3 dimensions is more complicated. Particularly here we're doing an animation in 3 dimensions. So if we look at the bottom of the code here, we see, right here, these are just the algorithm here, okay? And then these are the boundary conditions put in. So the algorithm is very simple. The rest of it is just plotting up and calculating all these fields. So let's run this code. May not touch anything and ruin it. Okay. And you see, this is the code. So we're starting off with a variation field for electric and magnetic in the x and y directions, and then we have periodic boundary conditions. So it vibrates, and then it just keeps repeating forever. And if you look at that, it really looks like a very nice 3-dimensional oscillation. This is not a movie. This is the actual code. You can change the numbers. You can play with the code. It's quite a feat. Somebody else wrote it. I didn't. Okay. So let's go back. Okay. So here's the assessment. What do you have to do? Take the code. Who knows which version we give you. Make sure that the boundary conditions vanish. Okay. So that's different. I've shown you periodic boundary conditions. Try this code out, making sure the waves vanish on the boundary conditions. Okay? So that's different. You should get some other kind, like standing waves, I would guess. Okay? Show the effect of these boundary conditions. I gave it away, but you may not get that. Test the Courant condition. Okay? See what instability looks like. See how different the wave looks when you change the sizes, how much you can get away with till it blows up. Now do something new. Okay? Put a dielectric slab inside the region, and piece of rubber or something. Okay, what happens at the boundaries? What happens within the slabs? Do you get reflections? Does it really work? And thank yourself that you don't have to do this analytically, because these things are always such a mess. You could make it a round slab if you want, and then get a more complicated geometry, something you'd never solve otherwise, but in the real world might well happen. Try other initial conditions. We gave you those very simple ones which we knew had to lead to nice waves. What if you just started off with a pure electric field varying in space and no magnetic field? Well, a space variation of the electric field should give you a time variation of the magnetic field. Time variation of the magnetic field means that it changes in time, so that even though it may have been 0 at first, at a later time, you get a magnetic field. Well, then if you have a magnetic field which is varying, it in turn will generate an electric field, so you should still get some kind of waves. In this case, you should get both right and left pulses, two coming out. See, analytically, that, see if that happens. And then finally, investigate the resonator modes for plane waves. Okay? So have boundary conditions, the waves have to vanish. Try to put plane waves that just fit in. See if you can set up a resonator. So what else can you do? One extension is you can say, what about circular polarized waves? Okay, we started off with the electric and magnetic fields together. What if we start off with them, not together, somewhat out of phase? Well, we can do that. Okay, so here, here we give you a code for same code, but starting off with the initial conditions, the phase, it's just a phase question, that should produce circular waves, circularly polarized waves, and if we run it, F5, it's running. And here you see, and for some reason the color is gone on my screen. I'm not sure what it looks like on yours. Probably. But you'll see that there's a rotating circularly polarized wave. So the rotation is the time variation of this, and you can see the electric and magnetic field. So again, somebody's worked pretty hard to get this to look so nice. You can try other fields. So go ahead. Don't put your fingers in any sockets, but do a little electricity and magnetism research. This could be state-of-the-art work people are doing in microelectronics now and in thin slab work. This is a kind of algorithm they use. So you can get a job. Bye-bye.